So this is good, and a lot of success of reinforcement learning actually happens when it's combined with deep learning. And it also enables the high-dimensional input. So it actually enables vision RL where you can have pixel at the state. It also well handles the partial observability. But then this gives rise to the problem of interpretability. So as soon as you have a neural network and a black box, then it's difficult to understand how these decisions are made. So these are very critical in high-stakes applications, for example, in healthcare or autonomous driving. Here I give an example scenario of XRL for medical decision making. Let's say you have an RL agent that learns an optimal policies. Now this RL agent has access to many sources of data. Let's say it has to electronic records, it has lab results or medical imaging, any other data. And then it recommends certain treatments by some probability. Now what would be interesting for, let's say, the clinician is that to also understand what this RL agent is doing. So you usually kind of either train something or you plug something to provide some explainability how this decision is made. And then you give some reasoning. Let's say you would say this treatment A selected because it was efficient in some similar cases. And then the clinician looks at this explainability and it kind of increases the trust. This is clearly has pros and cons. So if the explainability is, let's say if you're providing some sort of explainability in terms of confidence as well, then if your model is wrong and the confidence measure is also wrong, it somehow fools the clinicians by giving explainability that was not correct. So there are some researchers that says providing explainability, if they're not correct, it's actually dangerous because then the clinician relies more on your method. So now coming to XRL, why is that important? Again, a lot of critical applications, especially in RL, they demand transparency. So let's say in healthcare, if you have a treatment, you would like to know why this decision has been made. In autonomous system as well, it's very important. It's good for safety, for understanding and debugging. In finance, we would like to have compliance with some regulations. And in human AI collaboration, we would like the human to understand the agent to better trust the agent. Now, how is that different from supervised learning? So there are three very key differences. The first one is that we're doing sequential decisions. So at each stage, we take an action, and then that influences a lot how our trajectory kind of starts behaving from the beginning. Whereas in image classification, things are very simple. So you have an input and you have an output. We also have the problem of temporal credit assignment. So it often happens that you take a lot of action and you visit a lot of states, but the reward comes pretty like late at the end. Let's say you're dealing with, if you're working in medical domains, you probably know mimic data set. The sequence of data is pretty long, but at the end it just says whether the patient survived or not. So the reward comes very, very late, but when you want to do the credit assignment, it's very difficult to go back in time to see which one of these actions is very important. Now, the other issue is that we also learn through the trial and error, which means we don't really have the real ground truth. We take a lot of actions and say whether this fails or not. This is very, again, different from supervised learning. And then we have this exploration versus exploitation, where if you're familiar where you're exploiting your policy, you always listen to your policy, but that comes with this cons that you're not exploring anything else in your environment. And when you're exploring a lot of things, then clearly you might get more failures. So here I tried one way to organize all these XRL methods. So some of them are based on visualization. So they just show what the agent is doing, what are they seeing, what are these values. The second one is based on policy extraction. So if we, for example, make our policy, let's say if your policy is neural network, and then you can distill this neural network to another model that's, let's say, ensemble of linear models or decision tree, then you can better explain how the policies made, the decisions are made. Some work try to find critical states, meaning that they try to say which state is very important for the decision to happen. So there's clearly a lot of states that are not important when you're taking, when the agent takes decision. There are also a group of methods that they do trajectory analysis, and in every explainability we also have counterfactual reasoning. So we would say, what happens if I have done this action instead of the other action? So now we show a bit of the visualization-based approaches. There's nothing very fancy here except just using some sort of T-SNE plots, clustering, or seeing where your neural network is looking at, what's important in your state. So the first type of visualization is that if you create heat maps. Heat maps are usually shown like this, so that it shows like, imagine you have growth, and you're in some sort of a good scenario where every time you take one step closer towards your goal, and then the value, the boundary of values is pretty clear. So if you're somewhere here, you're -6, -5. So these are some sort of heat maps in some realistic scenarios. So, if you, for example, color this, then you would also see which regions has higher value for your agent to optimize their policy. Now, here is another kind of scenario. If you're not going with the foot club or with your driver, then you can like skip the sand, or you don't get stuck in sand, and you can probably like go faster towards your goal. But then there is a risk that you don't catch it. So in this case, if you have certain kind of visualization, you can compare this queue of state and action for different actions, and then understand what kind of preferences is that. Or if you plot actually your agent, you can understand how these trajectories are made. And it also helps you to identify some sort of suboptimal actions. For example, you do not want to get stuck in sand as in like the previous, if the penalty is infinity, meaning that you really get stuck there and you cannot kind of get out of that state. So based on that, you can probably get some insights on how to define certain states that you do not want to fall into that state. Or they're usually called dead-end states. So in terms of explainability, it can be useful to identify these kind of states. So again, when it comes to this heat map visualization, you can debug suboptimal policies. We can understand exploration versus exploitation. So there's definitely the trade-off. There's always a point in between that is optimal, but we always need to try so many variables to figure that out. Then you can assess the safety and the risk. So you would see whether your agent learns to avoid these very unsafe regions. Let's say here, for example, is clearly a problem. And then you can detect whether there's an overfitting problem. So if there's a spark or these regions do not look very smooth, that also shows that there's some sort of unrealistic scenario. So here I talk about EQ networks. It's a very well-known architecture. So, and it's also pretty simple. It's where you have here you have a convolutional neural network of 3 layers, and then as input you just give the gain states. Usually like in computer vision you stack RGB, but when you're in RL you usually get 4 consequence frames and you stack it and then you give it to your TANknet. So it has a bit of an understanding of temporal information, but it's not really that long. And then the output is that is the Q values for all possible actions. So the policies that would be learned by this neural network. Now, what is the relevance for XRL is that it enables this kind of learning very complex games. Like it was for the first time that we could solve Atari game. Then again, because we're using neural networks, we have this black box nature, which we would like to understand where the decisions are made. And then we want to analyze these Q values and look at internal representation. We would like to know what each component is learning. And some of the methods that actually I talk about today is they use this DQN architecture. Some of them might be deeper, but this is like the vanilla nature paper that they have. So here is one toolbox. It exists in the paper, but sadly it has not been released, which looks pretty useful. So it has this top-down exploration framework for that provides the statistics, epochs, and trajectory and segments. So it shows like your overall training progress. It shows episode level statistics, and then also it has trajectory. So if you have let's say your agent has a big trajectory, some segments of this trajectory might represent different behaviors. Like if we talk about, so I have some examples. If we talk about half cheetah again, some segments might indicate stable running, some of them indicate falling down. So it depends on how the agent learns the stability. So this kind of toolbox also shows the segments for you. So what is good about it is that for a statistic part, if you can detect these learning phases, you can see whether some strategies are emerging with your agent, and then whether your policy converges. When you usually train an agent in RL, at the beginning, the policy is pretty random, so until it starts learning something optimal, it takes time. In some games, you need minimally 2 million epochs or something to learn. So anyway, these kind of toolboxes usually are very useful because you can look what's going on with your agent. And then there's also provides epoch view, so it groups some episodes that have a similarity in terms of action and reward. It also shows behaviors, which ones were successful, which ones were not, and you can also see the consistency of your strategies. Here is an example again from the paper, because this whole toolbox is not released. So another thing that you can actually look at is you can look at your content filters to see how do they look like, and you can also have a visualization like a salience map, which are gradient based with respect to your last layer, which are your values. And then it also provides a view based on TCA, like a 2-dimension to see clusters of which states fall close.